Okay, thank you. Thank you very much. I'm Hirotaka Tanikawa from the Nagoya University, Japan. It's now very midnight of Japan, but I'm very happy to joining here. And on behalf of the all SEM board member, I'm very happy to seeing you all here. And also I hope everybody being safe under the current circumstances of the COVID-19. And on behalf of the all SEM board members, I also all welcome you via Zoom and also via YouTube, actually. So we actually originally planned the 2020 ISI SEM conference in Sendai, Japan in the last September, but of course, these situations that we canceled the physical conference, but we switched to this online conference. And so actually today, thanks to Paul, we have the quite interesting topic of the session 7 of the socio-economic metabolism and inequality. Thank you very much, Paul, for arranging all of that. And also thank you very much for joining the all speaker. And also thank you very much for joining all the participants here. So I hope you enjoy. And also if you have any interest about more about the SEM, socio-economic metabolism, and then you could join the ISIE and also join our ICM sections. So thank you very much, everyone. And back to the Paul. Thanks, Paul.
Thank you, Hiroki. I hope the feedback is now better with me. Can anybody confirm? So otherwise I will keep it very short.
Yeah, it's still there, but it's a bit less.
Yeah. Right. I'll try not to take too much time. Anyway, so welcome also from my side to this 7th session on social economic metabolism and inequality. Some housekeeping before. For those of you who are members of the section, actually, we will soon open a submission so that everybody can propose topics or propose talks for future events within the Perpetual Online Conference. We will write an email about this very soon to all members. So you see also in the corner of the screen that all the talks are being recorded and they will be posted to the YouTube channel of the ISIE later. We will cut out the discussion, so if you don't want to be on YouTube, it will only be the talks that are on YouTube later. Next thing is maybe, so we will do all the 3 talks in a row and then all of the discussion after that, also because of the recording. And I would ask you to raise your hand. I will monitor the participant list. You can also ask questions in the chat. Maybe it would be better if you ask them after all the presentations so they don't get lost in the chat. All right, so today's topic is socioeconomic metabolism research and resource inequality. As you're probably aware, the topic of environmental inequality has received increasing attention recently, both in the political but also in scientific discourses. In terms of politics, unequal access to resources and inequalities also in the environmental impacts is of course at the core of many of the bottom-up struggles for social justice and is also connected to many other forms of socioeconomic inequality. Then maybe in a more technocratic top-down political discourses, inequality is often understood or discussed more of a problem of public acceptance, for example, of climate change mitigation. So there's very different nuances of this here. But then also finally, you can also see the unequal distribution of resources as a numerical problem in a resource-constrained world where resource distribution is in the end a zero-sum game. And we will hear talks on all of these aspects of resource inequality today. For SEM research, in particular, this means, of course, that if we want to contribute further to this debate, we need to extend a lot of our tools a little bit. So traditionally, we work a lot with national averages that cannot really see the distribution within a population, but more and more of the tools we develop do include this, and today we'll showcase some of these examples. Maybe because my sound seems to be bad, I would ask the speakers to introduce themselves. We will start with Diana Ivanova, after that, we have Joe Bozeman and then Ingram Jackard. And I would now just hand over to Diana to start the session off. Thank you.
Great. Okay, do you see my presentation? Great, thanks. Okay, so my name is Diana Ivanova. I'm a research fellow, postdoctoral research fellow at the University of Leeds. I finished my PhD at NTNU in Norway and have been living in Leeds here for about 2 years now. So what I'm presenting today is on energy, carbon, and inequality. And just I'll give a short background on what are some of the main issues that we're facing today related to climate and related to energy. What is the inequality that we see, or at least some evidence for that, how that links to other social inequalities, and then what are some policy implications from that. I like starting with emphasizing the urgency of the climate crisis, and this is a clock or carbon budget clock that is on the website of the Mercator Research Institute, and you could see that for the 2 degree scenario, for 1.5 degree scenario, we can quantify a carbon budget, and then based on the rate of consumption or the rate of emissions every year, we can quantify how long time we have left to exhaust this budget. So for the 2 degrees scenario, we see that we have less than 25 years. And for the 1.5 degree scenario, we have less than 7 years to completely exhaust all of the carbon that we have left to stay within safe limits. So basically, this is no time at all. And if you look at how global emissions have been changing over time, we see that basically they have been rising. This is what you see here is daily CO2 emissions from fossil fuels, and they have been rising. And the only times where we've noted decrease in emissions, it has been at a time of devastating crisis, the last example of which is the COVID crisis, and this is the red line, the red dip that you see on the graph. And it's completely depressing that we don't see any dips in emissions associated with ambitious collaborative effort on tackling climate change internationally. We just don't see that. We don't see absolute reductions in emissions. So in my talk today, I will be referring a lot to carbon and energy footprints and to consumption-based accounting. And I assume most are familiar with the method, but just a brief introduction for those who are not. If we, for example, consider the carbon footprint of a city, we're interested in the carbon embodied in the consumption of that city. And that may be produced within the boundaries of the city, or it may come from elsewhere. So that could be imported or produced internally. And we don't consider production within the city limits that end up consumed somewhere else. So basically, consumption is really what sets the scope here. And consumption carbon footprints, they're very unequally distributed spatially. This is a graphic that shows GTAP. So this is one multi-regional input-output database that is quite widely used, and we could see that the spatial distribution of carbon footprints is very unequal, and particularly the per capita CO2 emissions are even more unequally distributed. And we see that Europe, Australia, parts of North America, they become very significant consumers and emitters from that perspective. At the same time, countries in Africa, in Asia, their contribution shrinks from per capita consumption carbon footprint perspective. There are many drivers behind these spatial differences, and I don't have time to go over them, but some are economic, some are technical, some are geographic, cultural, but one that is very, very important one that is referred to a lot in the literature, that is income, because we see very, very tight correlation between income and consumption-based carbon and energy footprints. So this is a figure from the recent Emission Gap report by UNEP. And what you see in red is the contribution by the 1% richest people in the world. And those, so the top 1% income earners, they contribute to 15% of greenhouse gas emissions. That was their contribution in 2015. So there's really quite stark inequality that needs attention. The line on the left graph shows the per capita carbon budget in 2030, and there's been differences in how that is estimated, but it's usually between 2 tons CO2 equivalent per capita and 2.5 tons. In this analysis, they used 2.1. So we see that the emissions associated with the top 1% of income earners are more than 30 times that carbon budget. At the same time, the bottom 50% income earners have much lower consumption than what that budget would allow. And they could increase their footprint 3 times and still stay within the limits of those 2.1 tons. So we see really a small share of the world population that is over-consuming many times beyond what we could quantify as an allowance from the 1.5 carbon budget. And the vast majority under-consumes and has much lower footprints than what they would need to satisfy basic human needs. When we look at how those emissions have changed over time, and we focus on the dark green here, which is again the bottom 50% of lowest income earners, we see that their share, their consumption hasn't changed. The total consumption hasn't changed over time. But in the same period between 1990 and 2015, the share of emissions of the top 10% has increased quite substantially. And thus the richest 10% of the world have exhausted 31% of the carbon budget between 1990 and 2015. This is massive inequality, and it really shows that we're not, so we have a certain limited carbon budget left. We're not currently using it to increase and to improve well-being where there really needs to be improved because there's a lack of essential consumption there, and instead the carbon is used to satisfy for overconsumption of the highest emitters. I want to make a small disclaimer here that a lot of these results, they show consumption perspective, and any perspective has blind spots, and consumption perspective is great in some regards, but its blind spot is that of supply chains. And other analysis has shown that a very small share or a very small number of large companies and international corporations, particularly fossil fuel corporations, have contributed to the vast majority of emissions as extractors and as manufacturers. And one study in particular links 71% of cumulative greenhouse gas emissions to just 100 companies. So this again requires a lot of attention because it opens questions about agency and power and where power is centralized. And then what would be effective strategies for mitigation that would target a relatively small number of stakeholders. If we go into energy and how energy is distributed, we see that similarly to carbon, it is very unequally distributed worldwide. And these are results from a paper by Yannick Oswald and some of his colleagues. And if you focus on the table on the left, the indirect energy, so this is the energy that is embodied in the household consumption. About 45% of the energy, indirect energy use, is allocated to consumption of the top 10% richest and less than 2% to the bottom 10%. So again, we see quite stark inequality of energy. I really like the graph on the right because it shows very important dimensions that we need to be interested in. One is the energy intensity. So how much energy different consumption categories require per unit of consumption. And on the y-axis, we have elasticity. So that is how does the consumption changes as we get richer? Do we consume more or do we consume less of these goods? So the red quadrant on the top right, it shows luxury and high intensity goods. So those goods we really need to pay attention to. And there is a lot of transport related goods, so vehicle, fuel, package holidays, vehicles and air transport and other public transport, but particularly air travel is one that stands out from a lot of the literature as very energy intensive and hence carbon intensive and highly elastic good. So this is a category that will become much more popular if as income increases. So yeah, there's that requires attention. So why is energy inequality important? Well, energy is central to nearly every major challenge and opportunity that we face today. And we need to be concerned with inequalities in general in order to not further disadvantage and marginalize populations. So when we design environmental policies, we need to be aware of how these policies will affect different parts of the population, how would affect groups with social differences. And this is both a matter of effectiveness, so avoiding to address people that cannot engage with certain policies, and also a matter of social justice, so how to offer fair options for people that have particular needs. And with regards to that, I want to show an example of a study that Lucy Middlemiss and I are currently working on and hopefully soon submitting, where we looked into the energy use of disabled people and other economically active and economically inactive households. And we see that systematically disabled people had lower incomes, which translated into lower energy use. And also at constant income level, we still find negative. So this is from a regression analysis, just the disability effect. We still find negative effect, so lower energy use associated with health, insurance and recreation, housing, transport, hotels and restaurants, and other consumption. So even though there's a lot of evidence showing that disabled people actually have higher energy needs, and that may be home energy, or it may be mobility, or health related. They actually consume less energy, and that is partly because of their lower incomes, and that is and partly because of reduced access and exclusions in other ways. But this is just one example in which environmental policy really needs to consider how how, for example, price changes or the energy transitions in more broad terms would affect different social groups. I am almost finishing, so yeah, I hope I'm not running out of time. But so basically, at the end, I wanted to finish with what we need to do. We need to radically decarbonize energy demand and to reduce energy demand, but also pay attention to the energy and carbon inequality. And a quote from a paper by Elke Pilgrimer and Julia Steinberger that I think is really important is that we need to prioritize which directly serves human needs, that which directly serves provides human needs. So that could be access to healthy food, clean water, mobility, healthcare, education, and we should collectively establish what directly provides to our human needs. At the same time, we should focus much less or not at all on indirect provision. So what may or may not lead to human need, but it's unclear. So that could be growth, for example, profit making. And there is a really hopeful study by Joel Millward Hopkins and his colleagues that show that we could satisfy decent living standards and all of the basic human needs for a population of 10 billion in 2050 with less than 40% of today's global energy. So this suggests potential for massive reductions without necessarily reducing well-being, but we need to do this. This will be incredibly ambitious, and we need to do this with sweeping changes in consumption, widespread deployment of advanced technologies, and the elimination of mass global inequalities. So it can be done, but a lot of political and social will is needed, and that is key. Finally, what is our job as researchers? We need to be very careful about the kind of changes and policies that we're advocating for, because if we focus on marginal changes that cannot deliver the kind of reduction in emissions and energy that we need to see, then we will be further reproducing the status quo, which is already unsustainable and unjust, and in effect that would have quite harmful consequences. So we need to be very careful about how we communicate and what. Thank you very much. That's all from me for now.
Thank you very much, Diana. Interesting. As I said, we will move on directly to the next presentation, and please keep all your questions for the three presentations.
All right. Really good stuff, Diana. And thank you, Paul, for setting this up. Paul, if you could, don't mind, thank you. It's just the feedback. But I really wanted to jump into this pretty quickly. I'm Joe Bozeman, postdoctoral research associate for the University of Illinois at Chicago Institute for Environmental Science and Policy. I won't go into too much more intro for the sake of time. It is important to disclaim that we'll be talking about a lot of this material from a United States perspective and data framework with some global implications. But to align with what Diana was making mention of in regard to our limitations and how quickly we have to react, these planetary boundaries, which are science-based thresholds such as water use, land use, climate change, adaptation, stratospheric ozone depletion, we all know the stories, right? These things are going to limit our ability to maintain our ecological cycles in a manner that the whole planet can be resilient. And one of the things I think that gets lost when we think about these big carbon threshold and planetary boundary thresholds are the socio-ecological and socio-political dynamics. So I'll be talking about some of these dynamics using this framework. We'll split it up into three sections. We talk about now, where we're roughly at 7.8 billion people in the world. We'll also move to year 2050, where we expect 10 to 11 billion people roughly. And then the distant future, where I think it gets a little more ambiguous of what our population economy is going to look like. So let's start with now. And I won't go through all of these aspects in detail for the sake of time, but I am going to mention some highlight points. So within the US West Coastal region, just recently in 2019 and 2020, they had the worst wildfire issues within 18 years, almost 2 decades. And all of us know from a scientific standpoint, that's partly due to climate change. California alone had a 53% rise in blazes from year 2020 in comparison to year 2019. Mass shootings, and for the sake of argument, this includes 4 or more people who are killed by mass shootings. There were more in the US mass shootings in 2019 than there were actual days. Now, this isn't new news to a lot of folks that are listening to this, but it's important to mention there is a very direct racial hierarchical and socio-political dynamic to why these mass shootings persist within the US framework. COVID-19, the world is dealing with it, but the US, I think, is arguably underperformed based on many people's standards. Just February 22nd of 2021, we surpassed 500,000 deaths in the US alone. And a lot of this has been argued to be connected to the US political situation, infighting on the adoption of mask wearing, based on if you're a Republican or a Democrat or independent. And plus, this population economic growth curve is directly connected to just population density in itself and travel. We have to think about how we can mitigate these things moving forward. Suicide dynamics. In the US, there is a distinction between how suicide rates are trending. Middle-aged white men within the US have the highest rates, and making gun laws more stringent to mitigate some of these suicide rates and other mass shootings are being stifled to maintain racial hierarchy. And there are legitimate research and a lot of books and other kinds of materials to support that sentiment. Hashtag BLM, the Black Lives Matter movement, which I think for many years seemed more like a centralized US effort for Black and brown folks, but I think in 2020 really expanded to be respected as a global network. It was founded in 2013 after the acquittal of Trayvon Martin's murder, and reignited in 2020 after the George Floyd and Breonna Taylor murders. And then of course, there were countless other stories that led up to the consensus around hashtag BLM and all the other intersectional dynamics it supports. The US Capitol insurrection or riot was driven in part by fears of demographic changes in the US, racial ethnic fears, political misdirection, and climate change dynamics connected to job loss. So all these things are threaded in the socio-ecological and socio-political framework. And then more recently, we had the Texas freeze, where lower temperatures actually stymied the operation of their electricity grid. And I won't go into the details of it, but just know that this was driven in part by climate change skepticism by key stakeholders within Texas state and the national framework, and a lack of preparedness. Not only that, I think this example in particular exemplifies some of the food, energy, water nexus challenges of now and the challenges we're going to have to prepare for in the future. And it intersects squarely along socioeconomic and racial and ethnic dynamics, because marginalized communities tend to be disproportionately impacted by events such as these. So we're going to move to year 2050, which obviously we're not there yet, but I do want to just establish some dynamics that we're all going to have to address as scientists and citizens of the world. So those planetary boundaries I made mention of may be breached or adversely impacted. And this also aligns with what Diana was arguing. We could see continued ecosystem challenges. I won't go through all of them. A lot of you are aware of them. Heavy precipitation in some regions, increased drought and precipitation deficits in others, hot extremes, winter extremes in some cases. Food, energy, water challenges are likely to follow. And then there's obvious socio-political challenges that may intensify or emerge. And then issues that we haven't even thought of yet. We're going to have to begin to prepare for and figure out how to navigate if we're going to adapt to climate change well. And then what about the distant future? Maybe in year 2100 or year 2200, what will happen? So to frame this, I'll talk about 2 population growth and economic theories that are foundational to a lot of the ways people approach these concepts. And we'll start with the Malthusian theory. I won't take long explaining it, But just notice that on the y-axis, you have cumulative population, or excuse me, cumulative pollution. And then on the x-axis, you have population year. So that red line indicates, based on the Malthusian theory, if population increases through the years, we're just going to have cumulative pollution increase. And we're going to see increase in greenhouse gas emissions, increased land use, increased water use. That's essentially unsustainable. But there's another concept that aligns with this Malthusian theory, and that is, if we're ever going to reach a pollution level and a behavior change that is going to help us stay within those planetary boundaries, we're going to have to see a population decrease in effect. I don't know how that happens within the Malthusian theory framework, but that is how this theory works. Now, I think a more widely accepted theory is this cornucopian Bossert theory. Another way of explaining this for those who are into this population growth theory is the environmental Kuznets curve, which has gained some traction, I believe, in the 2010s and here more recently. But it's an inverted U-shape. On your y-axis, you have pollution per capita, and on your x-axis, you have pollution year or population year. And essentially what this means, if you split it up into 3 areas, is that that first section there represents our industrial economy. Most of the world, at least most of the high income world, really saw an industrial revolution and saw a boom there. And most people argue that we're now meeting that saturation innovation point where our population per capita obviously has to decrease for us to meet all of these degree C standards and the like. But how do we do that? How much effort are we actually putting into that? And then the downward curve here on the right side would be a healthy adaptation. And I'm going to get back to this theory here, but I want to talk about global urbanization trends just here real quickly. Obviously, I made mention of 7.8 billion people being on the earth now, 10 billion by year 2050. But when you think about these percentage of urbanized populations, which is represented there on your y-axis, the entire world is urbanizing based on these forecasted trends. And when you think about all of these socio-ecological and political dynamics I've already made mention of, mixed with an urbanizing population and a higher aggregate population total, we're going to meet something that I like to call social densification phenomena, or just social densification, which is a play on the term urban densification, which is a widely accepted framework when it comes to urban systems. And when we think about this social densification, how is this going to potentially impact these theories and these trends that we're noticing within the US and through implication throughout the globe? I argue that this social densification phenomena is emerging to be a very prevalent thing that I don't think we've categorized and encapsulated within a framework such that we can approach addressing these issues. So I'll quickly run through a socioeconomic study on US food, energy, water equity across racial and ethnic lines. This is a flow chart of the method. I won't go into the details, but just know that the data you see will be cradle to farm gate land, greenhouse gas, and water impacts that represents the expanse of food consumed in the United States across major food groups, which in this case are called socioeconomic status food groups. For those that may want to come back to this in the recording, here's the equation. You can obviously look to the publication. But to get to the results, these are US mean results per household within the US. And if we look at the land category, and the units here are square meters per US dollar spent, the protein food group emerges as having the largest land impact per US dollar spent. So this means that roughly 4 square meters of land are disturbed per US dollar spent in the protein foods category, with grains following. Let's look at greenhouse gas. This gets interesting as it goes. Dairy emerges as having the largest greenhouse gas impact per household. And this is a kilograms of carbon dioxide equivalent per USD, with protein following second. What about water? We see that grains emerges as having the highest liters per US dollar spent impact compared to its other food group categories. But I made mention about racial and ethnic dynamics. So let's look at it from a racial and ethnic standpoint. Now, we don't look at every single subgroup. There wasn't enough refined data to do so. And I do want to mention that the data you'll see here is statistically significant. Before I get into the data itself, this US food expenditure analysis suggests that on your left side, you'll see that the Black, Latinx, and white subgroups are represented. And that Latinx subgroup, that middle bar you see, actually spends more of their overall income on food than their Black and white counterparts. And on your right side, you'll notice that the average income before and after taxes is the highest for the white subgroup. But if we look at these Black, Latinx, and white subgroup data points when it comes to food consumption impact rates, the Latinx subgroup emerges as having the highest land disruption per dollar spent as a subgroup compared to their other counterparts. It's the same for greenhouse gas, the same for water. That's really interesting, right? When we think about what we may intuitively believe when it comes to who impacts the environment more. But there's a thought experiment that if we were in real life, I would split the room down the middle. And even if you don't like it, I would tell everyone that you have to be an American citizen for this thought experiment. And the folks on the left side, as you can see here, make more money, and the folks on the right side make less money. Now, when we put these subgroup specific food consumption impact rates within their proper categories, on the left side, we would have white households, but you notice that their land greenhouse gas and water impact rates are lower than their Latinx and Black household counterparts, which are on the right side. But what's interesting about this is if you recall that food expenditure analysis slide that we just talked about, these white households actually can spend aggregately more on food and therefore impact greenhouse gas and water in particularly at a higher rate than at a higher aggregate level than their Latinx and Black households, despite the fact that the Latinx and Black households have higher rates. So what that means, there are some socioeconomic and political conditions that are leading to these differences. And there are also some economic buying power implications. And that leads me quickly to the implication slide. Reductions of food spending in the protein and grains category could have the largest mitigation in land and water impacts. And reduction of food spending in dairy could have the largest mitigation in greenhouse gas emissions. But I think it gets even more interesting when we come to potential policy proposals. Why not incorporate these food consumption impact rates into SNAP? And by the way, for those that may not know, SNAP is essentially the food stamp program within the US, into SNAP education for consenting folks who are willing to understand this information and accept it. And we should incentivize certain demographic groups to purchase more fish and plant-based foods based on the findings in the numerical outcomes of this study. And then lastly, let's use this information to support food access and health issues in the USDA dietary guidelines. There are tangible reasons and social pressures of why these concepts exist. And I think this is a good step towards developing enough policy to maybe start curbing our activities to get to that Malthusian curve and go more so to the Bossert dynamic. So with that, I really appreciate your time, and I'll be ready for Q&A later.
Thank you very much, Joe. It was very interesting. And we directly move on to Ingram.
Okay, you can see it. So thanks, Joe and Diana. Those were two great presentations. I'll start here. My name is Ingram Jackard. I am a researcher and PhD candidate at the Potsdam Institute for Climate Impact Research, PIC, and this is in the Social Metabolism and Impact Future Lab led by Helga Weiss. And I'm here going to present some recent work done by Helga Weiss and Peter Paul Pickler, right, and Johannes Töben and myself on investigating the energy and carbon inequality corridor for a 1.5 degrees Celsius compatible and just Europe. And this work is in journal article form and to be submitted this week. And so I'll here present the main results and conclusion. But the first time we're presenting it, at least. So I'll start by recognizing a dual challenge that exists, and this has been presented by both Diana and Joe as well, of course, not only globally, but also within regions such as Europe and within individual countries, namely how to achieve the 1.5 degrees Celsius Paris Agreement climate change target, while at the same time providing everyone with an amount of energy that is considered the minimum for a decent life. And what makes this especially challenging are the current levels of economic, energy, and carbon inequality. And there's a growing group of literature showing just how large these inequalities are, including recent work by Diana, our first presenter here, specifically for Europe, but also some of those studies that she presented in her talk as well. And in our work here, we aim to build on this and investigate what European inequality in household final demand expenditure, household energy footprint, household carbon footprint means for achieving those dual goals in Europe. So a maximum decarbonized energy supply compatible with 1.5 degrees Celsius and minimum energy use for a decent life by the year 2050, as well as what achieving both would mean for the level of possible inequality. To do this, we constructed household energy and carbon footprints per harmonized European expenditure decile for the year 2015, using 28 European countries. We did so using the environmentally extended multi-regional input-output model EXIO-base, decomposing household final demand expenditure and the household energy use and carbon footprints by national income group using data from the Eurostat household budget survey before distributing them into 10 European expenditure groups. I'll first present those inequality results, which will lead up to the final figure, where we situate these results within the 1.5C scenario and minimum energy use for a decent life literature. So this first figure shows our European inequality results for 2015. Panel A is household final demand expenditure per European expenditure decile. B is household energy footprint. C is household carbon footprint. And the important thing here is that expenditure is more unequal than energy, which is more unequal than carbon. Why is that? Because the energy and carbon footprint intensities of expenditure are higher and more variable in the bottom 4 deciles especially. And so energy intensity is in panel D, carbon intensity in panel E, and then the carbon intensity of energy is also higher in the bottom 4 deciles, and that's panel F there. Now, when we look at the energy and carbon footprints broken down into 5 aggregated consumption categories, we see that housing is really the category where the bottom 4 deciles have much higher energy and carbon intensities. And so the footprints themselves are almost equal across deciles, or even higher in the bottom 4 than in the top 6. These high housing intensities and footprints in the 4 bottom deciles are mainly because of inefficient and dirtier domestic energy supply and demand technologies for heating and electricity generation in especially Poland, Bulgaria, the Czech Republic, and Romania. Meanwhile, the mobility category is the most unequal, similar findings as in the work by Diana and others, followed by other material goods, then other services, and finally food. Now, I will say here that our normalized unit of analysis is household per adult equivalent, not per capita, which you can see on the y-axis there. And this will be relevant later on. But this is how the Eurostat household budget survey controls for household population size. And we wanted to stay within that framework for this study. Now, at this point, we wanted to investigate these inequality results in the context of different decarbonization scenarios and minimum energy use for decent life estimates. And in order to do this, we decided to remove the inequality in intensities that we saw in those first 2 figures here by giving all the deciles the same intensity per those 5 consumption categories as in the top decile, the 10th decile, the richest decile, that with the most expenditure. This is a counterfactual showing that if all deciles had access to and used the same technology as the top decile, The 2015 European energy footprint would have been around 19 exajoules less than 2015 than it actually was. And the energy footprints in some of those countries, especially in Eastern Europe, would have been up to 60% less than they actually were. Now, here we finally situate this inequality within the various 1.5 degrees Celsius decarbonization scenarios. I will stay on this slide for some time here and go through it as this figure delivers the main conclusions of the paper. Now, in the upper right legend, you can see different scenarios. These are not all of the 1.5C compatible scenarios that exist, but enough to capture the range of different outcomes we felt. The 1.5 degrees Celsius compatible scenarios reach different maximum final energy supply estimates in the year 2050, based on different assumptions about how the energy mix changes, the size and speed of efficiency gains, the amount of carbon capture and storage deployment needed, and the development of socio-technological infrastructures. Beside each scenario in the legend there, you can see their maximum energy supply estimate in 2050. These were all originally in total gigajoules per capita, and here they are adjusted to household gigajoules per adult equivalent to compare with our inequality results. These scenarios reach final energy estimates for the world and regions within the world. So for example, the GEA efficiency scenario that you can see in the legend there found European final energy would be on average around 64 household gigajoules per adult equivalent in 2050 under the assumptions in that scenario. What we do is first take those higher scenarios as upper limits in this range of possible energy. Moving to higher final energy values than the highest scenario shown in the figure, so SSP2 1.9, means that you start to leave the 1.5 degrees Celsius compatible zone. Now, we were at first curious to investigate what happens to the energy use, especially of the bottom deciles, when our European energy footprint results are scaled down to meet these decarbonization scenario energy estimates on average. So from a 2015 average of around 270 gigajoules per adult equivalent, all the way down to, let's say, 94 gigajoules, as in the SSP2 1.9 scenario. When we did this, right, we can see that at current or 2015 inequality levels, even achieving the 1.5 degree Celsius compatible scenarios with the highest final energy in 2050 meant the 4 bottom deciles moving well below most estimates of the minimum amount of energy use required for a decent standard of living. Estimating minimum energy use for a decent life is of course challenging and doesn't lead to a single agreed upon number. There is a large range of estimates, anywhere from 15 gigajoules per person up to 100 gigajoules per person or higher. And we include in our scenarios list 2 more recent demand side focused scenarios, the low energy demand LED scenario by Grubler et al. from 2018, and then as mentioned by Diana, the decent living energy DLE scenario by Millward Hopkins et al. From 2020. These scenarios estimate from a more bottom-up approach how much final energy per person is necessary for a decent standard of living, and what would global final energy then be if this minimum energy was met for everyone. These assume no carbon capture and storage, but they have very strong demand side assumptions, such as steep reductions in average living space per person and the amount of personal vehicle use or flights per year. The DLE scenario ends up at an estimate of around 15 gigajoules per adult equivalent. And we take this as the low end of our range of minimum energy use needed for a decent life. And the LED is higher for their world average at 27 gigajoules and their global north average at 53 gigajoules. So now in this figure, what you can see is first, on the x-axis, a range of minimum energy use required for a decent life. It ranges from 15 gigajoules up to 60 gigajoules. The space inside the figure can be thought of as contour lines on a map, where as you move from the origin in the bottom left towards the top right, the maximum average energy supply increases. The colored lines are the different scenarios with their different maximum average energy numbers represented in that space. And then the y-axis on the left-hand side shows the maximum possible energy use inequality when you select one of the scenario lines and a minimum energy use value. What the gray horizontal line labeled energy use inequality 2015 shows is the 2015 energy use inequality level after we gave all deciles the same intensities per consumption category as the top decile. Now, these inequalities are measured in 10-10 ratio, so the average energy use of the top decile divided by the bottom decile. And so the energy use inequality 2015 line is thus a 10-10 ratio of 7.6, meaning the top decile uses 7.6 times more energy than the bottom decile. So for example, if we assume a very low minimum energy use below 27 gigajoules, you can find where this is on the x-axis. Then if we go straight up to the energy use inequality 2015 horizontal line, we can see that only the top 4 scenarios would be possible at that level of inequality. And these all rely on some deployment of carbon capture and storage. If we use the value given for the global north at around 53 gigajoules as minimum energy use for a decent life, and you can find that on the x-axis, which still requires strong demand side measures, then inequality would need to be basically 0 in the LED scenario and more than halved in all the other scenarios. So the main point is then that as you go higher on the x-axis, i.e. as you provide more minimum energy use to all Europeans, to then also achieve the maximum energy supply that keeps Europe 1.5 degrees Celsius compatible means that energy inequality must be reduced. Now, to conclude, we argued that based on the results presented here, achieving the dual goal of a 1.5 degrees Celsius compatible Europe, where everyone enjoys a minimum amount of energy use, of course requires lower footprints in all European countries and almost all expenditure groups, especially major intensity reductions in the lower European expenditure groups and absolute reductions in the higher expenditure groups. But as we saw in the last figure, even under the bold assumption that the energy and emission efficiencies of all expenditure deciles converge, and demand develops as in the 1.5 degrees Celsius scenarios, it will also likely require a drastic reduction in the inequality of energy footprints. Now, there are many tools available here. So strong progressive carbon pricing could have a positive distributional effect, besides its effect on absolute emission and energy reduction. In addition, other distribution and transfer instruments, such as wealth and inheritance taxes or more progressive income taxes, will all have to be discussed in order to reduce the large differences in purchasing power and energy consumption within and between the countries of Europe, at least as long as expenditure remains coupled to environmental footprints. But considering the likely drastic nature of these inequality reductions, there will also likely need to be more fiscal and monetary leeway towards these dual goals, a discussion that appears to be gaining traction at the European Union level and at the European Central Bank. While this study now is Europe focused, of course, we contend that the main conclusions apply in a similar or even stronger form in the global, to the global achievement of climate and equity goals. And similar work could be done globally and within other regions and other countries. That's it for me. Thank you very much, and I'll stop sharing the screen.